بکنم ایشون ما رو نمیشنوه
بکنم شما نه.
Can you hear us?
Professor Saad, could you hear us? Professor Saad, do you have the voice?
No, he's writing no.
خب اینجا از این تریانگل اسپیکرش انتخاب کنه. از
اینجا نوشتم که اسپیکرشون رو انتخاب.
صدای ما رو نداره اصلا. صدای ما رو نداریم. آره ما صدای ما نداریم.
خب بهشون زنگ بزنم.
من با چک کردم.
خب بهشون زنگ بزنم.
دارید شماره‌شون رو؟
بله شماره‌شون دکتر نگهبان فرستادم.
خانم داوود صدای منو داری شما؟ خب خوبه. اوکی. مشکل از اون دوستان تو خودش هست.
Yes, we can hear you. What about you? Do you have our voice?
مشکل داریم دوستان چیز کنم.
نه که تو شماره شما.
بگیم شروع کنه.
چرا؟ خانم دکتر باید شروع کنه.
خب خانم دکتر شروع کنم ما باش چک بکنیم.
من بهشون زنگ بزنم.
گفتی بعد من نمونهشو بهت بدم.
اشغال.
شاید قطعش کرده که زنگ نخواد. این خانم دکتر شروع کنیم. این فاصله رو ما از اون برد کنیم باشون تماس بگیریم. شما فقط یک مقدمه
بده من پس دوربین بیام رو شما شروع کنیم میشه.
Good morning, ladies and gentlemen. Welcome to each and every one of you. It's a pleasure to be with you with the webinar of computed adaptive learning rates for Convergence. Before we get started, I'd like to express my sincere appreciation to all of you who generously helped us make this event happen. I'd like to thank Dr. Negahban, Dr. Pasalar, Dr. Zamani, Dr. Saha, Dr. Erfani, and all those who helped us make this event happen. The first presenter is going to be Dr. Zamani. Dr. Mohsen Zamani was born in Shiraz, Iran. He did his undergraduate studies in electrical engineering.
Can't hear
Shiraz
you.
University
Shall
of
I
Medical
start or
Science.
I can't hear.
So he received his degrees in electrical engineering. Then he received his master's degree with honors from electrical engineering at the National University of Singapore in 2009. He obtained his PhD degree under the supervision of Professor Brian Anderson from the Research School of Engineering in Australian National University in 2014. After that, he joined the Newcastle University of Australia as a research fellow. He is now at the Department of Medical Physics and Engineering of Shiraz University of Medical Sciences of Iran. Dr. Zamani, please take the floor.
Hello, everyone. Thank you for giving me this opportunity to share some thoughts about AI and how it can be applied for medical sciences. Sorry for wearing mask. I don't know whether I should say sorry or not, but we have lots of people here, so that's the regulation now. The way this presentation is going to be is that it would be a tutorial-like that aim to give some motivations and introduction about why we should go for AI and how it can be used for medical sciences, a bit of background, and some basic introductions. So if you have elementary knowledge about AI, then that would be a good point for you. How can I bring up my presentation? Share my screen?
Yeah. And share it there, right here.
All right. So as I said, my presentation would be more general, audience-oriented, and I think the Professor Sa's one would be more detailed and technical. So without any further ado, let me go to the details.
Try me to next.
Okay, good one. All right, so why AI? What is AI? Actually, we are using it in our daily life. Almost all of us have a Gmail account. In early days, you get lots of emails from a guy who were from country X and wanted to transfer, $5,000 into your bank account because he couldn't transfer it directly. These days, you do not get this sort of bothers. Lots of thoughts and work actually has been applied to spam detection, and now it's doing it automatically. Probably you notice now that when you write something in Gmail now, it detects what you're going to do next. There is an AI code there which is anticipating and predicting what you are going to write based on the context, the audience that you have, and so on and so forth. Probably you may get annoyed with Google Ads, whatever you write, then next day you will get something relevant to what you searched yesterday. So there is also an AI code there which helps Google to monitor you 24 hours, 7 days. Another application that we are using it in a daily life, it's in product recommendation systems, like in Amazon. Amazon, you buy something, then it tells you what you might be interested in. A similar program is Instagram or Netflix. Instagram suggests friends that you might have connection with, or anticipate that you may have connection with. We have a local version of these here in Iran, which actually works pretty well, like Digicala and Filimo. Filimo is a counterpart for Netflix, and Digicala, you can think it as an Iranian version of Amazon. So another example that I'm personally very fascinated about is the Tesla autonomous cars, and lots of companies actually are doing this, including Tesla. And the task that they're doing actually is very complicated because you are dealing with some objects which are statics, like the road barriers. But many of the objects that you are interacting with are dynamics, like the pedestrians, cars, the drivers, which in many countries are very unpredictable, and it's very difficult to anticipate what they're going to do next. And together with that, you need to do navigation, and that's also a task which is very, very non-trivial. Now, actually, these cars are complex of sensors and cameras. But at the end of the day, they have a very sophisticated AI core, which is going to anticipate and manage what's going to be the next by the engine and steering wheel. So after that, I would like to go to this part, that why do we need AI in medical sciences, and why actually it's worth looking at. I look at it from the three different angles: the growing market. Actually, it's becoming a very hot research area because of the reason that we have lots of data at our hand, and we have a sophisticated computation techniques and tools to handle. And I believe that the AI and the new technologies in medical sciences and medical technology provide a more fair and easier access for medical practitioners and also the patients. I got this figure from Accenture. It's anticipated that from 2014 to 2021, the global market of the AI in healthcare would jump to 11 folds in size. So it's a very big market. In some of the statistics, it says that the rate of the increase in the subscriber of these technologies increases by 30 to 40%, which is significantly high compared to the other markets. In relation to the research trend, we look at a survey paper which studies the AI in medical within the two index, Web of Science and Scopus. And as you can see, from 2011, it goes skyrocketing high and exponential increases in both indices. And so why do you think that AI in medical sciences in Iran has a very good potential to grow? Basically, 4 reasons I bring here. First of all, I think we believe that at the moment we have an acceptable global stage in this area. Then in Iran, you can relatively, compared to any other places, if you want to develop a technology, it can be it has much lower cost, both in development and establishment, currently speaking. And as many countries, here we have an uneven distribution of the medical facilities. As you may expect, bigger cities, much more facilities, rural area, much less. And this could facilitate significantly the, if we call this even distribution and fair access to medical care. So I bring up a table that supports the first claim. In this table, Iran is 12th after Turkey. And if you remove US and China, which are significantly higher in position compared to the others, then the positions of the countries are very much close. And then I believe with one step high and one step low, then the position will go significantly, your position will be significantly different. So to motivate and show some examples that how AI had been applied in practice, I bring up some examples now. First of all, these are examples that I saw Some of them I had interaction with. There is no advertisement here, by the way. The first example is the company called Kronikare, which is one of my friends in Singapore actually does this. What Kronikare does is that basically it has a device which you can see on the left. It's a gadget that can take a photo of the wound. These are the chronic wounds. And then it takes the image goes to the cloud. The practitioner has the access to the data through his tablet or a PC. And also there is a electronic medical record, which all this data has been restored and saved and can be retrieved. And the claim of the Kronikare is that they can assess the wounds, whether it's going to be healing or it's getting worse, within 30 seconds. Their businesses, as far as I know, actually are growing. They started in Singapore, now in, I believe, in UAE, UK. They're going to Australia as well. So to me, actually, their story was amazing. I had seen them growing very fast from 2014 till now. Another example that I want to share with you is a company called Oxipit from Lithuania. They provide a service which they call it chest eye. So the chest eye works like this. You upload your X-ray chest, and then within 1 minute or less than that, 30 seconds or so, they bring up a report which you can see in the left. The claim of the Oxipit is that they can detect up to 75 common diagnosis from the AI, from the X-ray, and in their website they claim that they got a €500,000 grant from EU to further extend their project from till 2022. Another interesting example that I came across is this Australian company called Harrison. They introduced this project called EV. Basically what EV does, they provide a camera, and it's on the embryo, and the aim of the EV is to increase the chance of the IVF success rate. So what it does, camera takes a video from the embryos and what's going on there, and then there is a deep learning behind it that helps the practitioners to select the embryo with more chance of success. And again, their claim is that they perform 30% better than the normal average embryologist. The fourth example is this company called CMOD, which is Australia and Singapore. I believe they started in Singapore and now moving to Australia. And what they do is that they focus on the ultrasound images and they provide a report and analysis of the vascular. Again, their claim is that they provide the result within a minute. And recently, as far as I know, they got $100 million investment from SoftBank, which is a Singaporean bank. The last one is our own work that I would like to share. It's an application named Diana, which actually we released it today. And the aim of Diana is to help the people with diabetics to control their insulin level and control their diabetes. So the next things that I would like to share is to briefly review a short history of AI, where it came from, and what's its taxonomy. So what is it that we call AI? What I found, actually, one of the difficult tasks is to make a definition about something. But loosely speaking, any entity that can solve and learn like our human brain, then we can call that an AI. So it can be a machine, it can be a software, or within software, it can be an application, or so on and so forth. So then you can say that's an AI. So the very quick history, we have the Alan Turing test that was proposed in 50s, and then we have the perceptrons and artificial neuron model that was introduced, I think, 43. The Turing test was actually very interesting, and it was saying that suppose that there was integrator do like some means of telecommunication, talks to two entity. One of them is a real person, and the other one is a machine. And then based on the answers, the people on the left has to judge whether the answer is coming from the machine or from the real human. So after the Turing test, there have been efforts. Before that, actually, there also have been efforts. And if we want to look at this philosophically, I mean, look at the AI, the roots of that goes to Greek and the Greek philosophers. But let's put that on the side. As then the term AI was coined, I think, 1955, I believe. But as many technologies were introduced, then we get this hype that this can solve any problem. But then it goes down slowly. That's what happened actually in 70s, that they call it the first AI winter. And then when the electronics and the boom of electronics increased, then people had more hope that, oh, now we can do more with AIs. But again, they overestimated the technology. And then what we got of so-called second AI winter. But as we become more advanced in the technology and communication, and also especially the computation, then people see more advances possible in using the AI techniques. And now I can say that this is the magic of our current time. And wherever you go, you hear deep learning AI, deep learning AI. Because one thing that is changed significantly now is that we have more data and we have more computation power, which we didn't have before. So some advances that have been made allowing this time, we like deep learning, Alpha Blue, in I think it was 1997, who actually beat Garry Kasparov, one of the biggest chess player in the world, and lots of advances has been made. One thing that I would like to share with you here is that there are terms that sometimes we use them interchangeably, but actually they are referring to different things. And this Venn diagram actually designed to make distinguish. We have the AI, then under AI we have machine learning techniques. The group of the AI techniques are much more than the machine learnings. And below the machine learnings, among other techniques that exist within the machine learning, then we have deep learning, which is now a very hot area to both technologists and scientists. And a term actually coined, like I think 7 years ago, called data science, and or data scientist. And the data scientist or the data scientist is the person who has knowledge of all these techniques, plus he knows some probability theory and some programmings, plus algebra. Okay. So let's look at this a taxonomy of AI and what is included. So techniques within AI. So I want to make a point here. Now it is very hard to put an edge between different techniques, because now we have the combination of techniques applied to the same problem. So, but if we want to be very traditionalist, so to say, AI techniques can be seen in the 4 categories. Some of them are logics, like fuzzy or pure logic. Some of the techniques can be put under the evolutionary computation techniques, like Ancolony, genetic algorithm, and so on and so forth. And some of them are really probabilistic theory, Gaussian mixture models, graphical models, and so on and so forth, again, can be seen under this umbrella. And then a category which we're going to talk next, in particular, is the machine learning techniques. Machine learning by itself can be also seen in 4 categories: supervised learning, unsupervised learning, semi-supervised one, and reinforcement learning. So we will going to see very quickly what these are. So before that, let me share with you this slide. Traditionally, what we used to do was this, that we used to give we had a data, then we put some programs inside our computer, then that gives an output. For example, that could ranges from a very simple if-else rules to a more sophisticated control techniques. But we had the data, we had the program, we expected the output. But in the machine learning slide, we reverse and reassemble the framework. And how it's done is that we have the data, we have the output, then we give it that one to the computer, see what the program should be, and then we use that program. So the paradigm that we use here is going to be like that. We start with the problem always, right? So we have the problem, then we use a machine learning technique, and then use a set of data to teach or train this learning model, and then evaluate the result. If it is satisfactory, then we're good, we're going to launch. If it is not, then we start from the beginning. We look at the problem again, see what aspects we might have neglected. We modify the model, we train it again, and this cycle is done many times until we get to the satisfactory output. So let's see what the different branches are in very short. So the supervised learning are basically, we look at the labeled data. So for example, here we have circles, stars, and squares, and they're well distinguished, and we want to separate them. In medical applications, we mostly looking at supervised learnings. We have data from the patients and data from the normal person, and then we look at the new data. We want to see whether that's patient has this is a patient data or a normal data, or we look at the cancer data. Is it benign or not? Then we make this distinguish. The data is labeled already for us, or if it is not, then we have someone to do it for us. But in the unsupervised learning, the data is not labeled. We know that here, for example, we want to cluster these circles. We know that there exists a cluster, but this data is not labeled. So that's the realm of unsupervised learning. As you might expect, the supervised, semi-supervised learning is the technique that some part of data is labeled, some part is not, and then we want to deal with this scenario. So the larger portion is not labeled, but the smaller one is. And finally, the things which I like very much is the reinforcement learning. Reinforcement learning simply works based on our human learning techniques. So how do you learn riding a bicycle? You ride a bicycle, then you fell, and then your brain learns that if I push the pedal by this force and I balance my body like that, then I may fall or I may not. Then that's how you learn. And in the program, in a computer program, you do the same. You make a reward. If the computer does something right, then it gets a reward. And if it doesn't, then you punish it. And that's how it learns how to solve it. For example, the Go game that I think it was done in 2014, that the world champion of the Go game was defeated by a computer. They use reinforcement learning. It's very suitable for control purposes and games. So in the supervised learning, all problems that we have, we can see it in two sets: the regression problem and the classification. So let's see what the regression problem is and what the classification problem is. So I got this a slide from Andrew New. The regression problem is this, that you are looking for a map from your input X to your continuous output Y. So the term continuous here is very important. For example, here you have the data of the price of the house within your neighborhood in last, I don't know, 5 years, based on the square feet or a square meter. And then you want to know, if I have this amount of money, what sort of house, what would be the price of the house that I can get. So that's a sort of regression problem that one may deal with. On the other hand, the classification problem, as the name explains, you want to group one or more set of labeled data. And you want to group the malign from the benign, malignant from the benign cancer result, and these kind of examples. So what are tools available to us? I want to review them very quickly. One of the common, the list can be more exhaustive than this. I just look at 3 of them, which are very common. decision tree, support vector machine, or SVM, and ANN, or artificial neural network. The decision tree is very good for when you have a finite states. In this example, you have, they call it party problem. Then you have a decision, you want to make a party. Then you have a decision to make, whether you want to have it outdoor or indoor. Then whether it's going to be rainy or not, whether it's going to be sunny or not. Then you use the data, the data that you have, you train the tree, and when a new data comes, then the program is able to tell you with this input what sort of result, with which probability you will get. So that's simply a decision tree. It's very good when you have a finite states, and you know the output of each state and the action that you take based on that state. Another technique is called SVM. The SVM actually is designed to find the optimal hyperplane to segregate two sets of data. But when we say optimal, what do we mean here? Here, optimal in the sense that the hyperplane is to be in this equally distanced from the two set of data. Here, L3, even though if you look at L1, L2, and L3, the L1 actually doesn't a very good job in making a segregation between two set of blue and red circles. The L2 does that, and also the L3. But L3 is placed in an equally distanced place between these two set of data. The interesting thing about SVM is that it ends to be a convex problem. And since it's a convex problem, then we can claim that the solution that we get is a globally optimal solution. So what is ANN? ANN, or artificial neural network, actually provides you a black box that maps your input X to your output Y. And it started by mimicking a natural neuron, right? So how it does, it's that in the natural neuron, you have the cell which gets the input from a dendrite and then gets the output through the axon to the next neuron. And they do the same in the perceptron, or so-called artificial neuron. You have the inputs, and each input has the weight. Then you have a nonlinear function that operates on the summation of all these outputs multiplied by the inputs multiplied by the weight, and then you get an output. So as simple as that. We call this a perceptron, right? Then if we put several perceptrons together, then we got a neural network, like what we have in the natural version. The very right-hand side, the black set, we call it an input level or input layer. That's where the input comes in. The layer which is between the input and output, we call it hidden layer. And the very right input, we call it the output layer. If we have more hidden layer, then we got what we call deep neural network. So the deep NN is not something very new, actually. But what's new is that we have a capability to deal with that in a real time and in a computationally possible way, which we didn't have before. Okay? So areas of research that someone can look at for applying and making a contribution to medical. First of all, actually, is the radiology. We have lots of methods of imaging and lots of methods of diagnosis. And actually, there are lots of opportunities down there for someone to tackle. What is fashionable now is deep learning. You use deep learning, you have this technique of imaging, and you want to do this diagnosis. And what actually we have an issue with here locally is that we have lots of data, but this data is not labeled properly. I don't know about other places, but here we have this issue. Another area which someone can look at is the well-being. Now, there are lots of gadgets that monitors your health, and it gives an intensive amount of data that someone can work with to help people be healthy and live a better life. In orthopedic, one of the things that people have looked at before and requires more works is the fracture detection, whether that can be done in an automated way, or bone tumor diagnosis. In ophthalmology, now there are lots of projects going on that people look at the retina image and could conclude about different diseases that a person can have or is going to develop. So there are lots of projects going on. And I know there are lots of disciplines and new opportunities that I may not have mentioned here, but are down there. For example, one of the works that we are doing is a project that we are doing with a colleague of us that actually have been done before in some countries, and we want to try to enhance it, is that you use ECG signal to or ECG images that is available to help people and prevent actually from dying, because sometimes it happens that by simple misdiagnosis of an ECG signal, a person had a heart attack, but this is misdiagnosed and a person simply dies, which is really sad. One of the things that I would like to talk about now is the leading figures and leading industries. So a person who is interested can follow this and learn more about their advances and their most recent developments. This list can be very exhaustive, but some people who are very active and well known is one of them is Andrew New from Stanford and also works with Baidu. He has a very well known machine learning course on Coursera, and also on his webpage in Stanford, he has a very interesting materials that someone can use to learn more. Ian Goodfellow has a very interesting book still on deep learning. Professor Benigo from Montreal University, they do amazing works, and there are lots of materials on their group webpage that can help the interested readers. Jan Likon and also Jeffrey Hinton from Toronto University. You can find lots of good materials from Hinton's website that can accelerate someone's learning process. But who are the leading industries here? As you might expect, these are the big companies, big tech companies, right? Google with its DeepMind. Microsoft has an AI lab, which actually very advances in this new technology. IBM Research does a lot, especially in medical. And Baidu, which is less known to people. This Chinese company, actually, I can say, in some aspects, it's a very competitive to its American counterpart when it goes to the AI techniques and AI technology. Some useful resources that someone can actually use to expedite the learning process and also expand his or her knowledge. One of them is Kaggle, which is very useful. It provides you with many data sets in many areas. Plus, to that, it gives you an opportunity to share your codes, learn from the other people's code, and people could comment about what you have written. And also, it provides a competition that you can, on different topics. For example, lately had this competition on COVID, and people will participating in that. The Google and its teachable machines, amazing tools. You can just drag and drop your elements, and then it gives you a Python code, and it's very good tools when you want to rapidly prototype something. And the Google Colab, which allows you to run your codes on Google machines. One thing which I found interesting is the Amazon AWS AI. And I noticed that many companies actually use Amazon service. For example, it gives you a pre-specified codes and tools for natural language processing. Also, it gives one thing that I found very interesting. It gives you a forecasting tools that you can use in your to prototype something very easily and quickly. That brings me to the end of my talk today. I would like to thank you for your attention. And as I said at the beginning, I wanted to have this in a form of introduction or tutorial way. Again, thank you, and I think we will have the question at the end, right?
We can have it at the end.
Maybe if you have a question now, we take it. Huh?
Yeah, I do have a question matters.
Okay. So they tell me that we better have a question at the end. I will be here if you have anything. I will be more than happy to answer. Thank you very much. Bye for now.
Okay. Thank you very much, Dr. Zamani, for your very nice presentation. We really enjoyed that. Now we have our second presenter, Dr. Senahashu Saha, who obtained his master's degree in mathematical and computational sciences at the Clemson University. He also received his PhD from the Department of Applied Mathematics at the University of Texas at Arlington in 2008. After working briefly at his alma mater, Dr. Saha moved to the University of Texas as a regular full-time faculty member in the Department of Mathematical Sciences. He's a senior member of IEEE, and he is now an associate professor of machine learning at the Department of Computer Science and Information Systems at Birla Institute of Technology and Science, Goa Campus, India. Hi, Dr. Saha. Can you hear me?
صداش مشکل داره. یه لحظه. دوباره بپرسید.
Hi, Dr. Saha. Can you hear me? I guess yes, he can't hear me.
Yeah.
Oh, okay, that's great. How are you, Dr.
Yeah,
Saha?
I can hear you. Can you hear me?
Oh, that's, yeah, sure. Very well.
Hello?
Hello, Dr. Saha. I guess it must be
Hello, can you hear me?
afternoon. Yeah, sure. I can hear you.
Hello?
I have,
Hello, can you hear me?
yes.
Hello?
Dr. Saha, I can hear you.
Can you hear me? Hello?
Yes, I can hear you, Dr. Saha. Okay, I
Hello?
can hear you. Yes, I can hear you.
Yeah, can you hear me? Hello?
Yes, Dr. Saha, yes.
It's better that I...
Dr. Saha, I can hear you very well. Okay, maybe you can start your presentation, okay? Please start your presentation up, and after that, our attendees can pose their questions to you. Hello, Dr. Saha. I can hear you very well. I guess you don't have my voice.
Hello? Hello? And my audio is fine.
Dr. Saha, will you start your presentation? Please start, Prof.
Hello? Hello?
Hello, Dr. Saha. I can hear you. Please
Hello?
start your presentation. Okay.
Yeah, hello. My audio is fine actually. Yeah, hello.
Okay.
Okay. So you okay, all right, great. Okay. Yep. Okay, sure. All right, I guess that was some glitch, right? It's okay. So good morning, assalamu alaikum. I hear a lot of beautiful stories about your beautiful country, Iran, and I hope someday that I could actually make time and visit your country. There are some personalities which I am aware of and very fond of from your country. One is
Okay.
yeah. So you can hear me now? Can you hear me now? Hello? Can you hear me now? Hello?
Yes.
Can you hear me?
Yes.
I think it's better that I don't use my webcam, because that seems to be a problem with the internet connection and all that. But can you hear me?
Okay, we are all ears.
Yes,
Please
Professor.
start.
Okay.
Now they have.
Okay, all right, yeah. Do you see my white screen, my whiteboard? Hello?
Yes, sure.
Do you see my whiteboard?
Actually, we see your PowerPoint.
Do you see?
Yeah. You want?
Okay,
you
all
want
right, great. Because
actually to use PowerPoint. Oh, we have it.
Yeah. I will use my whiteboard, so that's why I wanted to make sure. So anyway, so shall I start?
Sure. We are all ears, Dieter.
Okay. Thank you so much. Thank you so much, Professor. I sincerely appreciate your invitation, and I'm very happy to give a talk. Although virtually, I have heard beautiful stories about your beautiful country. And good morning and assalamu alaikum. There are a couple of personalities from your country which I am very, very aware of and fond of. One is I really like Majidi's movies, and and there is this brilliant mathematician Maryam Mirzakhani, who unfortunately passed away, also from Iran. So anyway, so my talk today is sort of assimilating modeling approaches in machine learning. Okay, and I'm really glad that Professor Zamani gave a talk before I did, because he actually built the foundation and platform for some of the things that I wanted to talk about. So he mentioned a few things about deep learning and neural networks, right? And he gave a very nice overview. And he did talk about two kinds of problems: regression and classification, right? And when Professor Nagban invited me to give a talk, and he asked me what I would like to talk about, and I told him that I would like to talk about some of the deeper understandings of deep learning, which are applicable directly to medical sciences and a lot of other branch of sciences and engineering. Okay, all right. So let's begin. So the title of my talk is computing theoretical adaptive learning rates in deep learning, right? So I mean, if you really want to dissect the title of the talk, it's like this. I mean, so I do care about some theoretical measures of learning in neural networks. Okay. The question is why? I mean, why would anybody care about such theoretical measures? Now, as Professor Zamani mentioned, there are two kinds which people usually dabble in. One is a regression problem, right? One is a regression problem, and the other kind is a classification problem. Okay. The question is, are these related? Is there a connection between the two? So is there a connection between the two? Is there a connection between the two? And the other question is, can we kill many birds? Can we kill many birds with one stone? Okay. So First of all, what's the difference between a regression problem and a classification problem? A regression problem is actually where you want to estimate or forecast some quantity, right? We estimate or try to estimate, forecast some quantity, right? Some output, okay? Hello? Yeah, Professor? I have already shared it. I'm using the screen. No, I'm using this whiteboard, right? I'm using the whiteboard. So hello? Can you hear me? I mean, I have already shared my screen, okay?
Okay, please push next button, okay?
Which button?
As Adobe. Please use the Adobe application and then push next.
Next.
Yeah.
There is down below the page on the left, you can see a downside arrow. Can you see that?
Okay. No, see, no, Professor. The thing is, okay, I'm sharing the screen. I have shared my screen, so I just want to use the whiteboard.
Okay, so you can change your slides when something finishes. You can change your slides from bottom of the page. Okay?
No. I understand that. I understand that, Professor. What I'm trying to tell you is that right now I'm writing or using my stylus pen, and that is on a whiteboard.
Actually, we cannot see that. We cannot see that. The only thing that we can see is
right. So I mean, can your technical support make me? Can your technical support see?
Yeah.
Yes, sure. We will.
No, I mean 1 minute. Okay. Hang on. I just see there is
here.
Okay. See, otherwise it will become sort of difficult, because if I'm not able to use my whiteboard, I was previously able to use my whiteboard. You know. See, let me.
If you want to share your screen, please.
I'll just. Is there a way that I can use my? Just hang on.
Okay.
So I'll just share my screen. Okay. So you tell me whether. Yeah. Please don't do anything. Let me just try to share.
Okay, so there is a little triangle next to the
I have started sharing my whiteboard. Can you see it now?
No, not yet.
Hello?
Hello, we can see your your whiteboard is not.
We can hear you.
Here.
Yeah, I think something is going on. Just hang on there.
Okay, let me share my screen. Okay, I have clicked on share screen option. Okay, and I don't know, nothing is happening. Nothing is happening. Okay, nothing is happening. I think no, right. I know that you can see my slides, but I mean, you cannot see my whiteboard, right? I mean, yeah. Just a moment, because it's loading again. Yeah, it's just loading, right? So I have never used Adobe Connect before, so I mean. So that's why, I mean, yeah, okay, all right. Let me see if you can.
Okay, now
it will pop up. Hang on. Are you able to see now?
Yes.
Yeah.
Yeah, are you able to see?
Yeah, sure.
Hello?
You have your whiteboard now. Can you hear us?
This is my whiteboard? Yeah, okay, great. Okay. Yeah. All right. Yeah, so sorry for the Yeah. So you can see my whiteboard, right? Okay. So let me, I'll just write something. Okay. Can you see the cross that I just made on the left with the red pen?
Yeah, yes, sir. Yeah.
Okay. All right. Okay. So I'll just go ahead now. Okay. All right. So what I was saying was that, when we talk about some theoretical measures of learning in neural networks or deep learning, right? Why would you care about something like that? Okay. Is there some tangible outcome that we can quantify, right? Or is there some measures that we can actually compute which says that, okay, if I do some theory in neural networks, the real mathematical stuff, then there is some reward for me at the end. Okay, otherwise why would I do that? Okay, now in order to understand such measure of learning, such theoretical measure of learning, we need to understand a little bit about regression problems and classification problems. And if there is a connection between the two, is there some way I can connect the two? Turns out, yes, there is a way via neural networks I can actually connect a regression problem with a classification problem. And therefore, I can actually use the same theoretical measure to actually solve a regression problem as well as a classification problem. So to begin with, what is a regression problem? We just estimate or forecast some output. So for example, let's say, I have some gene expression data, right? And human genome project, I have some gene expression data. Okay, all right. And where there is some output variable, okay, y, which is dependent upon a bunch of input variables. Okay, a bunch of input variables. Now, what I want to do is the following, that, well, these bunch of input variables are actually accompanied with different sets of coefficient values, which we don't know a priori. And what we wish to accomplish via regression problem is to be able to measure, like a sort of forecast a value of y and compare the forecasted value with an actual value. So there is a y actual that we already know, and then there is a y predicted. Okay, all right. Now the efficacy or efficiency of your regression method will depend on how small this is, right? So if this is small, which meaning your error in prediction is low. Then we will go back and say that the model is a good fit. Okay? The model is a good fit, pretty good fit. Okay? It's not as simple as this, but this is at least how we begin. Now, when we talk about a class, so what really happens is there is one value. Please note that there is one value always that we are predicting. Okay, just one value that we are predicting, or we are coming up with scoring based on a bunch of other values that we already have. And so these bunch of input variables are actually accompanied with, they actually come from the data that we have. Okay, and we can also call it a training data. We can also call this as a training data. Now, when we talk about a classification problem, okay, it's something like this. Let's say we are trying to find, once again, I'll take an example from health sciences, and this is a problem in India. I'm not sure about Iran. This is a major problem in India, particularly in the rural areas of India, is that a low birth weight problem. I'm not sure, how critical this is in Iran, but what I have heard is that at least the public healthcare system in Iran is much better than what we have here actually in India. That's what I have heard. I'm not sure whether, how far I'm right or wrong, but this is a low birth weight problem. So, newborn babies, being born with really low birth weight, or there are babies which are born healthy and born normal, their birth weights are fine. right? So what happens is, based on a bunch of critical input factors, like for example, in every trimester, whether the mother has gone for an ultrasound, if the mother is healthy, if the mother is having nutrition levels, like whether the mother is taking carbon, folic acid and things like that, right? Okay. Based on the family history, whether there is a history of diabetes, whether there is a history of high cholesterol and other health problems in the mother, or there is some hereditary problem present in the family. So based on a bunch of such factors, and also there is this level of education, right? People who are educated, they understand that you need to take care of yourself during the pregnancy, correct? Okay. Otherwise, it could lead to a lot of problems. So this low birth weight problem is itself a major problem, because a lot of the babies which are born with low birth weight eventually do not survive for long, right? So this, instead of framing this as a regression problem, what we can do is that we can think of a two-class problem, where class 1 is the LBW, or the low birth weight babies, right? Low birth weight babies. And then class 2 is where, you have normal babies. Okay? By normal, I mean babies with normal weight, born with normal weight. So this is a classification problem. So it's like this. So you have some, some threshold, let's say, you have some threshold right over here, you have some threshold here, right? And you say that a very simple logic would be, if your y value, it's basically you are actually converting a regression problem to a classification problem. So your y value, which is your birth weight score, if it is greater than this threshold, so let's call this threshold t, right? If it is y is greater than t, it's actually normal. If y is less than t, it is actually low birth weight. Okay, so it's a classification problem. All right. So in order to learn the classification problem properly and being able to predict, right, the outcomes properly, you need to have a corpus of training examples, which is exactly what we talk about in regression problems as well. Okay, so both of these kind of problems require a significant set of training examples for your algorithm to train and learn, right? Okay, and therefore, based on the learning procedure and the amount of data that you can feed to the machine, it should be able to make an efficient prediction. Okay, so the training is a very, very important step in machine learning or deep learning. Okay, now when we talk about training in deep learning, because that is the aim of my talk today, when we talk about training in deep learning, we need to consider a bunch of different things in the context of the title of my talk. Okay, so when we talk about training, once again, I'm grateful to Professor Zamani for bringing this up in his talk, is that he said that, we have the luxury of a lot of training data these days. Okay, all right. So the first point is that we have a lot of data. This is a good thing, right? You'd imagine this is a good thing, right? Okay, and then we also have, thanks to AWS, Google Cloud, GPU computing systems, we do have a lot of compute power. Okay, we do have a lot of compute power. But what is the downside of it? What is really the downside of having a lot of data and a lot of compute power? You do have a lot of machines, right? You do have a lot of data. So there are two things that would actually, I'm sure you have heard of the free lunch theorem, right? Which means that there is actually no free lunch. Okay, so which means if we do have the luxury of a lot of data and a lot of compute power, there are some downsides that will be accompanied with this. One is, how much infrastructure are you spending in order to train your algorithm properly? So that means, what is your CPU or memory utilization? Okay, how much CPU or memory are you consuming? And the other thing that you also need to keep in mind is that how much carbon are you emitting? Because we need to be responsible, right? I mean, the Americans can always talk about controlling carbon emission in other countries, but they never really do care about controlling carbon emission in their own country, right? Okay, so it's easy to advise others. So when we are worried about carbon emissions, we talk about carbon emissions all the time. I mean, why don't we train our algorithms in such a way that the carbon emission is less? Okay. Recently, I mean, Professor Zamani has also actually talked about NLP. I mean, he has talked about very large compute systems built by Amazon for NLP purposes. Recently, there is an MIT technology review report, okay, and it says the following. They actually took a deployable machine learning, deep learning model for natural language processing and something which is production ready. You can use it for as your chat bot, airlines guys talk to you, right? I mean, whenever these days we try to contact the airlines, I mean, through an online thing, the other end of that conversation is always a bot. It's a chat bot. It's not a real human talking to you, right? So such an implementation ready, production ready system. So there was an extensive study by a couple of faculties from University of Cambridge, some 6 months back, where they reported the following, that in order to train and build a product ready natural language processing system, the amount of carbon that you are emitting is actually equivalent to 6 cars. Just listen to this, 6 cars running for 30 days non-stop, 24 hours. So imagine that for a second. You have trained a machine learning algorithm, you deployed it, you are getting good results, but at what cost? Your cost is that much amount of carbon emission. Okay, all right? And so there is also this issue of interpretability, which means, and since this is a medical university, you would know much better than I do, that in a lot of the times, the prediction algorithms, the predictions that the algorithms come with, I mean, you doctors usually, I mean, a lot of times you doctors don't actually agree with those. Okay, all right. So therefore, the training part of your deep learning algorithm is really, really critical. And this is where the theoretical measures of learning come into handy, because they help you actually process a very large amount of data using cheaper compute power. Okay, all right. So if we really want to at the end of the day, if you want a summary from me, what is the takeaway from my talk? The takeaway from my talk is the following, that I would want to do theory in such a way that it actually helps in some really useful practical considerations, such as help in lesser carbon emission and help your lesser, much cheaper CPU and memory utilization of your machine. Okay, about whatever machine you are using. I mean, in fact, I mean, if you have gone through my research profile, you would see that most of the times I actually do not prefer to use a very compute heavy infrastructure at all. I would like to write algorithms in such a way that they would run on my laptop, which has only a 4 GB RAM, compared to a very high-end infrastructure which requires a minimum of 128 GB RAM, 32 times faster compute processing capabilities compared to my laptop. Okay, all right. And mind you, my laptop is not a cheap laptop, it's quite an expensive laptop, but it's still, I mean, okay, so this is the direct consequence that I would like to, I would actually want you to understand. Okay, this is the direct consequence that I would like to talk about. Okay, all right. Otherwise, there is actually no point in talking about theory. Okay, absolutely none. All right. Okay. So let me, and by the way, I will, along with my slides, I'm saving each one of these images. So at the end of my talk, I will email you all of this. Okay, so that you know. I'm saving this. All right. So therefore, there is a clear connection between, at least what happens is, so to summarize, so just as a summary, before I get into all of this, is that regression and deep learning are related. Okay, number one. And number two, the deep learning algorithms should accomplish good results in a responsible manner. Okay, this is what we call as responsible AI. Okay, all right. Okay, so now let's just quickly, give you the model description of a regression machine, right? So typically what is this, like I call the output or the hypothesis as this in a regression problem is like this. I mean, you do have a bunch of parameters, okay, all right? And these are, all of these guys, these x1 through xn's, these are actually your input, okay? And therefore they come from your data. What are these guys? These guys are the coefficients that we don't know. These guys are the coefficients that are unknown to us. Okay, and this is what we call as a model bias. Okay, so I mean, what I mean by that is that what you are trying to do is that, let's say you have a bunch of data points. Okay, you have a bunch of data points like this, like this, like this, like this, right? Like this, scattered in the two-dimensional axis. And what you are trying to do is you are trying to learn a model, right? You are trying to, let's say, you're trying to learn a model like this, okay? A straight line, that is, okay, which will sort of account for most of these data points, in the sense that there would be some error. You cannot imagine a line which will actually fit all of these data points, right? And each one of these data points, as you can see, if I take any data point, it's actually can be written as xi comma yi, correct? Okay, where your xi is the values in the horizontal direction and y is the value in the vertical direction. And this is what you actually predict. So you actually do know a lot of the data points that exist in your two-dimensional space already, correct? So which means that you have a lot of training data already. And based on that training data, you also know the corresponding y values. Now what you are supposed to do is that if based on this you have a model, then I give you a new data point. Let's say I give you a new data point somewhere over here, okay? This is a new data point, all right? And the job is to see how well this line, this model that you have come up with fits this new data point. So in other words, what you have to do, that you have to sort of measure a loss, okay? Or you can also think of this in terms of cost of your model, okay? So what is a loss? Your loss is actually nothing but the difference between your actual value and the predicted value, okay? All right, so if I want to write this as a loss, I mean, if I want to quantify this as a loss, then this is how I actually write this, is that if I have n number of training examples, my loss is nothing but the hypothesis, right? And this is actually this is your hypothetical value. I mean, your values that you predict from your hypothesis or your model. This is the actual value. What you do is that you take the difference of this and square it up, right? And sum it over all training examples that you have. This is your loss. Okay. Now imagine this h of x is actually expressed in terms of these guys, right? So in other words, what you got to do is that you got to write this h of x as in terms of all these thetas, and remember all of these thetas are actually unknown, right? You got to measure those. So how are you going to measure those? So the efficacy of your model, your efficacy of the regression model is directly dependent or directly proportional to how well you have estimated the coefficients theta 1 to theta n. And this is directly related to how small the loss g of theta is. Because if your loss or error is a minimum, then that means your model is a very good fit, and your model is a very good fit if you have measured the coefficients well. Okay, so one way of doing this, so therefore, I mean, your prediction problem or regression problem, your prediction or regression problem is actually equivalent to a learning problem in a neural network setting. Okay, now how do you do this? Now typically when you look at this loss, it's a squared function, right? And we know that any squared function actually looks like a parabola. Now what is a parabola? If you don't know a parabola, forget about it. Okay, you don't need to know. A parabola is actually typically looks like an and a bowl, like the bowl where you would traditionally have your shorbas, right? So this sort of looks like a shorba bowl, right? And it looks like this, assuming. Okay, now what does it mean? It means that, I mean, what you typically do is that this is the trajectory of your loss function. So typically, as you can see, I mean, I sort of start traversing from any side of the graph as a loss function. If I'm here, I cannot say my loss is very small, because the idea is to minimize the loss. So what I do is I will actually start traversing in both directions, right? Okay. And if I am able to reach here, if I reach here, as you can see, this is the lowest point in your shorba bowl, and this is where your loss will become almost zero or minimal. You cannot do any better than this. That's the whole point. Okay, all right. So this is like, traveling, along the inner surface of a shorba bowl or a soup bowl, right? Okay, where your motivation or intention is to reach the lowest point. Okay, how do you do that? You do that by minimizing this function. Okay, you do that by minimizing this function, and you do that by, we call this, I mean, when we are actually moving in this direction, we actually call this a gradient. Okay, your gradient of the loss function. Your gradient of the loss function. Okay, all right. And typically after every step, this has to be an iterative state, right? I mean, you cannot really reach there in one shot. So you have to actually try multiple times, right, until you actually reach the minimum point or you succeed. Okay, so this is an iterative process. So this gradient is an iterative process. Okay, which means you got to repeat yourself, is an iterative process. And how do we achieve this iterative process? We achieve this iterative process in the following manner. We say that this is an iteration, some step number. This could be 1, 2, so on and so forth, right? And this is just its previous step number, okay, minus some constant times a partial derivative with respect to your loss function. You really don't need to know, I mean, how exactly we do, but just try to understand this. So the way things work is that whenever you are regressing or classifying, right, I mean, the idea is to minimize the loss. Loss between what? Loss between actual levels and predicted levels. Whenever you are doing a classification problem, that is, your intention is still the same. You are trying to find out the exact levels. Based on the training levels, your validation, when you do the validation process, you try to find out what is the test level. So the difference between your predicted level and the actual level should be minimum. And that is what is achieved by the loss function. And how you do it? You do it in an iterative manner, where this is, now you can think of this in the following manner, that let's say j equal to 2. Okay, if j equal to 2, I mean, you have updated your position of any of these thetas that you are estimating, right, in the following manner: theta 1 minus alpha delta del theta 1 of g. So if you know the first value, you iterate it, you keep on iterating this until you actually cannot improve any further, which means you stop. When do you stop? You stop when at an arbitrary point, at an arbitrary step, right, the difference between the current step and the previous step is really, really small and you cannot improve it any further. And that is how you minimize the loss. Now, here comes the theory. So this rule is called as gradient descent rule. Gradient descent. Okay, all right. Let's note one thing. Here is this guy, okay, here is this guy, which is actually some parameter alpha that we don't know. Okay, this some parameter alpha that we don't know. Typically, so that will be my next slide. So let me save this first. So what did we say about gradient descent? We said that this gradient descent is nothing but so this is my loss and this is a parameter that I set by some heuristics. And this is the problem of deep learning. Okay, why? Why is this a problem in deep learning? The reason why is this a problem is the following. Now let's think of a neural network. Okay, all right. So let's think of a neural network where you have bunch of, so it's an artificial neural network. Okay, it's an artificial neural network or ANN where you have a bunch of inputs. Okay, and then there is an hidden layer in an artificial neural network, one hidden layer, okay, where there are some nodes, right? And then let's say if it's a regression problem, there is just one output node, and that will store the y value. Okay, what we typically, like according to Hinton and Bengio, whom Dr. Zamani has mentioned, I mean, we begin by the fully connected neural network, which means everything is connected to this. Okay, all right. And then, okay, so here when you are moving from left to right, you have a forward pass. So what do you do in a forward pass? You use some activation unit, you use some activation to trigger such that your neurons fired. So these guys are all neurons. Okay, so these guys are neurons. All of these guys are neurons, right? So neuron is fired. So use some activation function, and then it goes, so you fire it in such a way that your input data is connected to an hidden layer. You use the same activation function here and pass it on to the output layer. So what happens is, typically you have, there is a target, right? Target or the actual value. And what you have done here is actually you have done a Y predict. Okay, all right, based on the neuron firing. And then what you typically want to look at is the difference between Y target minus Y predict. And you would want this to be as small as possible. Okay, as small as possible. Now, you would expect that, okay, fine, if I do it right, I mean, and this is purely chance, right? If I do it right, if I have the right combination of this, and so each one of these edges are actually connected by weights. So you assign some weights, okay, and these are also arbitrary. I mean, we have no control over these weights, right? Okay, so typically what happens is, I mean, you have a combination of these inputs and the weights, and you pass it on, and then you pass it on, and magically you arrive at a predicted value which is exactly same as the target, no problem. But if you don't, then what happens? You have to go back. You have to go back. Okay? All right. Now when you go back, this process is known as back propagation. Okay? Now when you are going back, why are you going back? The only reason why you have not been able to achieve a value which is close to your target value is because you have chosen these weights to be wrong, correct? Okay, so these are wrongly chosen, right? Okay, so these weights are wrongly chosen. So these weights are wrong. So if these weights are wrong, what do I need to do? I need to update the weights, correct? How do I update? I update by using the gradient descent rule. Okay, so I'll rewrite the gradient descent rule in the context of neural networks, and it is this, that I update the weights wj plus 1 equal to wj minus some alpha delta, right, wj of the error. Okay, because whatever error that you are incurring, is because of wrong choice of update. So you need to reduce this error, okay, and the only way you can do that if you update the weights appropriately. Okay, so this is the gradient descent update rule for the neural network. Once again, you see that I have this problem. This alpha is chosen empirically. Okay, we really do not know what sort of alpha should we choose, right? Okay, and therefore what happens is, now since you have a lot of data and you have a lot of compute power, you can actually go this forward pass back propagation many times, hundreds and thousands of times, no problem, because you have a large compute infrastructure. But mind you, the side effect or the downside of that, so many iterations going back and forth, is that you are taking a lot of time to train your machine, you are using a lot of compute power, you're using a lot of memory, and therefore you are emitting a lot of carbon. Okay, so how do we do this more efficiently? Okay, so how do we do this more efficiently? How to do this more efficiently? Okay, that will be the next question that we need to discuss. Okay. So here is the learning process. Learning process, efficient learning, therefore a choice of alpha by some solid theory and not no guesswork. Let me tell you, this is the problem I have with most neural network architectures proposed by Bengio, Hinton, and others. Okay, I mean, what they did was that they did not think about these problems. They proposed architectures, they kept on complicating the architectures by introducing new and more advanced architectures. Okay, and the issue that we face in the deep learning theory community now is that how to explain why certain thing works and certain things don't work. Okay, so let me ask you a question. I mean, someone says that I choose a value of alpha 0.1 and it has worked on a particular data set. My question is why? Then he comes back and tells me, oh, you know what? For some other data set, this value did not work. So you know what I did? I did alpha equal to 0.01. And this worked. So this is the problem. See, I have no problems in guesswork. Sometimes you have to guess. But what is the cost of guessing? The cost of guessing is hundreds and thousands of iterations that you are actually wasting. So instead of guessing, we set theoretically computed adaptive learning rates. Okay, and learning rates that will be adaptive as you keep on from one iteration to the next iteration, it will be adjusted automatically. There is no manual override, there is no manual oversight, right? But these learning rates have to be computed very, very carefully. These learning rates depend on the kind of loss functions that you choose in your neural network. Okay, so in order to, because I don't have a lot of time, what I would like to say is that everything depends on your loss functions. Okay, so if your loss function is Lipschitz, okay, if your loss function is Lipschitz, which means the following, okay, which means that for a function f and input xy, a Lipschitz criteria is the following. If you really want to interpret this, is that you take two inputs and you compute the difference between the two, okay, and you also compute the difference of their function values. Okay, so what is happening is that this guy, because eventually this is what you are computing, whether you are doing regression or whatever, this is what you are computing. So these function values are actually controlled by or bounded by the difference between the input values here and some arbitrary positive constant, which is known as the Lipschitz constant. Okay, how do I use this Lipschitz constant for this adaptive learning rate? So my alpha, I choose my alpha as the inverse of the Lipschitz constant L. The moment I do that, I really don't have to worry about alpha is equal to 0.1, alpha equal to 0.01, whatever. Okay, but this has to be, we have to be careful, because if my loss function is a squared loss function, my Lipschitz constant is different. If it's a other kind of cross loss function like a cross entropy, it will be different. If it's mean absolute error, it will be different. For each kind of loss function, these Lipschitz constants are different, and so therefore their learning rates are different. Important is that this learning rate does not depend on your data, not at all. Okay, it just depends on what kind of loss function you are choosing. Okay, all right. So let me now go back to so let me just also save this, and then I'll go back to the slides, because okay, so I'll just share my document now. I hope. Yeah, it will pop up now. Okay, so I mean I have a lot of examples from astronomy, but I mean you can use this in whichever way you want, right? I'll just go straight to the loss function. Okay, and it also turns out, I mean, these loss functions have a lot to do with differential equations and chaos theory, but I'm not going to talk about those, right? So this is what I was talking about. Okay, so this is what we call as a bandit optimization or a beast optimization. So we're talking about learning rate, and we already know what a gradient descent rule is. For many inputs, I mean, you have to actually think of a set of partial derivatives which we call as the Jacobian, but you don't worry about that. So what you do is that if you set, now the question is, I mean, you may ask me the following: why did you set your learning rate as the inverse of a Lipschitz constant? There is also a theory behind it. I have shown in a paper recently that if you set your learning rate as the inverse of a Lipschitz constant, then the weight changes that we incur are actually become small. So I really don't have to remember. I mean, if you think of that neural network picture that I drew, right? I mean, when you are updating the weights, your new weight, if it is drastically different from your old weight, I mean, you have the danger of going outside the landscape of your problem and then come back again, right? So in this way, we can actually force the weight changes to be smaller than or equal to 1. That is not the only reason. The second reason is, if I choose my learning rate in this particular manner, then I can show that for a desired accuracy that I wish to accomplish, I can actually finish the algorithm in a certain number of iterations. So there is a theoretical result that I was also able to prove. Okay, all right. Now let me tell you also another upside of this. So, and this could actually work not only, so you have 2-3 considerations, right? I mean, you have to be able to match the state-of-the-art accuracies, which you do, right? Also, you really do not have to handcraft your parameters. You are not wasting time or effort in choosing or changing your parameters. It is automatically done by you by a formula. Okay, all right? And then you gain significantly in terms of some performance metric gains, which is across multiple data sets. In fact, for the low birth weight LBW data set, as well as gene expression data sets, specifically for the gene expression data sets, I can tell you that all the state-of-the-art architecture performances, they had taken like 1,200 iterations to converge, meaning 1,200 iterations to actually get to an appreciable level of accuracy. We did it in 90 iterations. Can you imagine? which somebody is doing taking 1,200 iterations, and this particular method, based on theoretically computed adaptive learning rates, we are able to do the same thing in 90 iterations, at least 20 times faster. Okay, sometimes it is really fast. I mean, really much more faster than this. And the reason why it's faster is because it is adaptive and it is automatic. There is absolutely no intervention. There is no need to change the weights as well as the learning rates as we go. Okay, so typically, if you run the code, you will see that the first value of the learning rate is actually typically large, but then it drops drastically as you keep on improving your loss bounds. Okay, all right. There are some other things, like there is a very critical role of an activation function as well. Okay, if you don't choose a proper activation function in the forward pass of your neural network, you are once again going to get stuck in a local minima, right, or something like that. So we wrote a new activation function, and we proved a lot of theoretical properties to show that once again, just like the learning rate. Okay, because if you look at this particular activation function, right, let me point this out, right, if you look at this particular activation function, right, this particular activation function, I don't know why the pointer is not working anyway. I just wanted to point here. Yeah, right. So you see that there are two pointers. One is k, one is parameter, and one is alpha. Once again, the natural question arises is that, do I know the values of k and alpha before? No, I don't. So do I need to do again a guesswork of k and alpha? No, you don't. So because depending on some functional properties and using some advanced mathematics, we can actually figure out the exact values of k and alpha for which your activation function will work properly. Okay, all right. So this is once again another important application of important reason, because I told you in the beginning of the talk that if you prove a theorem, if you do some theory, there has to be some strong motivation behind doing such theory, and after you have done the theory, your application and the results that you see have to be really remarkable, much better than what you have already been able to do or what others have already been able to do. Okay, so we wrote a bunch of activation functions. So the idea is that when we have done all of that, and there is a lot of theory, okay, when you have done all of that, so in the forward pass you use my activation function. In the backward pass, instead of guessing for your learning rates, you actually use a theoretically computed adaptive learning rate, right? When you do these things away, what are the takeaways for you? It's that it saves you the number of iterations or number of tries to converge. Okay, your accuracy, precision, recall, and other performance metrics are at least at the same level. Okay, and so far we have applied it on 13 different public data sets, from astronomy, from healthcare, from computer vision, okay, and from anomaly detection, industrial systems, so on and so forth. Also, if you compute the CPU and RAM utilization, you will see, that the CPU and RAM utilization are also at least 50% better compared to the other methods. Okay, all right. So this is why we call it parsimony, because people like us, like people like me and you, like people like guys living in India and Iran, we have some limitation on the compute infrastructure that we can use. We can't really buy a multi-million-dollar compute machine just to run some experiments on neural networks, right? So this is really relevant for us. Okay, all right. So we have done this on a number of astronomy data sets, like extrasolar planets as well as star galaxy quasars, and also estimating redshifts of galaxies and so on and so forth. And here are some relevant publications that you can see. Okay, all right. And I think in the beginning of the talk, which is if I go to the in fact, first slide. I hope I have done it. Yes, I have done it. Is that the talk that I gave, the entire code of the talk is available in GitHub for you to use. Just go there in that particular directory and use this particular, my activation functions and the learning rate, and you can see for yourself how
thank
it
you
actually
very
helps
much,
you. Okay.
Professor
All right.
Saha, for your wonderful presentation.
So I guess this is a good time to stop, and I'll be happy to take your questions now.
Any clarifications? You can pose it to Dr. Saha. Okay, you can activate your actual microphone over there. You can raise your hands. Even if you have any questions from Dr. Zamani, he's here and he can answer you.
Can I ask Dr. Saha a question?
Yeah, sure, please.
Dr. Saha, thank you very much for your very interesting talk. I have two questions.
You can take it.
Thank you. One of them is that you mentioned that the rating that you set as an inverse of utility, which is constant, sometimes it works than the others. Does this sometimes mean that in some cases it works in a worse manner than the others? And if the answer is yes, have you investigated?
Yeah. Right.
Oh, sure.
No. Okay. Yes. Thank you. Good question. No, sorry, there was some communication error. I did not say that it works sometimes. I said that it works all the time, always. Okay. And the reason why it works is the following: is the two things. One is that when we are considering the decay in the loss, we considered in L2, and most loss functions are well defined in the L2 norm. Okay. And also the second point is that we have done this for all types of loss functions you can possibly imagine. I mean, you yourself are an active researcher in this area. You know that most of the loss functions that people use are either the mean square error or the binary cross entropy or the categorical cross entropy, right? You also know the problems of using these loss functions. Like, for example, if your input data distribution is not normal, and you continue to use a mean square error, because one of the reason of why using a mean square error is that you take a maximum likelihood estimation on the normal distribution and you arrive at the mean square estimation, right? So if your input data or if your error is not normally distributed, then this kind of loss function doesn't work. Okay, number one. When we talk about cross entropy or categorical cross entropy, it has been shown recently by a colleague of mine, Mikhail Belkin of University of California, San Diego, that the cross entropy loss functions also work poorly on low rank features. Okay, so instead, but then the problem is, I mean, you need some functional properties so that you can do the calculus, right? The nice thing about mean square error and binary cross entropy both are that they are differentiable. I mean, they are differentiable everywhere, right? But I have shown in a recent paper that even if you have finite singularities in your function, like for example, mean absolute error, which is an absolute value function, and there is a singularity at the origin, right? Even with a finite number of singularity, with an epsilon smoothing, you would be able to use the same formula for the loss function. Right? Of course, the derivation will be much more harder, but I've been able to come up with another formula exactly in the same spirit, and these I have been also able to extend to check losses and quantile losses. Okay, so now even if you have different kinds of loss functions which are non-differentiable, you are still able to apply this formula. So to answer your question, so far it has worked every time. I mean, there is not a single case I have encountered. I mean, you can see my paper published in Applied Intelligence, Springer Journal, and International Joint Conference on Neural Networks in July, right? Okay, and if you go to my archive, you are welcome to go to visit my archive. You will see those papers. Okay, so yeah. Variations of gradient descent, mini batch, mini batch, stochastic gradient descent. I have also recently tried it without a gradient, which means, I mean, I have used particle swarm, parameters of particle swarm to approximate the gradients itself, so that I get rid of this gradient updating procedure altogether. Thank you very much. This is currently, this is a manuscript which is under consideration for publication. Right. So, so yes, to answer your question, yes. I mean, we have also used it on standard optimizers like Adam and other optimizers.
All right. Any other questions?
So if you go to my GitHub repository, Dr. Zamani, you will see the implementation, and you can come back to me with further questions, and I would love to answer
has raised hand.
Your questions.
Please, doctor. Right. You're all ears.
Oh, sure. Thank you.
So I made him a presenter. Maybe he can.
Yes, Professor Nagavan. How are you?
Okay, would you please activate Dr. Nagavan's microphone? It's active. Okay, Dr.
You can also
Nagavan,
type your question in the chat box,
please
Professor
raise your
Nagavan, if
question.
you don't mind. I mean, because if you're...
He can type his question.
Okay, if you don't have a microphone, maybe you can type, actually chat in the chat box. You can type it. Please start chatting.
Or enable his microphone on top of the window.
Okay, where is it?
Yes, this is. Click.
Oh no, I see Dr. Nagavan's question now. He is asking what is hidden learning. Dr. Nagavan, this is not a hidden learning, this is a hidden layer. So what happens is, when you think about an artificial neural network, between the input layer and the output layer, there is a hidden layer that is being constructed. Okay, so this is sort of a mimicry, I mean, you can say a high level mimicry of how human brain works, right? So between the connections of your input neurons and output neurons, you need some sort of an intermediary processor, so that you can, otherwise what will happen is, if you do not have the hidden layer, you have just the input neurons connected directly to the output neurons, right? And so if you make a mistake, you are actually going directly back to your input neurons to update the weights, okay, which is what a very simple perceptron does. But if you have a hidden layer, what happens is, when you are updating the weights, your weights are updated first from the output layer to the hidden layer, and then from the hidden layer to the input layer. So it's more of a graduated sort of an updation. So this is just to facilitate the weight update in a gradual manner.
Okay. And I put the phone number of Dr.
I hope I have answered your question.
In the chat box. Okay, it's 0905 1867 086. Maybe you can be in contact.
Yes, I see that.
That's great.
Thank you. Oh, okay.
Okay,
Yeah.
that's great.
Right. I mean, I would appreciate if you email.
There's someone else who
Right.
wanted to
No,
type.
I would appreciate
Let
if you
me
can
see.
email
Okay.
this to me,
Any
and
other one?
I
Any other
will
person
email
to
back.
ask?
I will email back the international office
Yeah.
with the
No
whiteboard
questions?
slides that I have just made during the presentation. Right.
All
Okay.
right.
And you
Thank
already
you
have my
very much
slides,
for
so I think
listening. I once
that
again
should
want
do.
to
Okay.
thank Dr. Negahban for suggesting and directing this webinar in cooperation with Dr. Farouqi from the Virtual School of Shiraz University of Medical Sciences. Special thanks are due to Dr. Paslar from the Department of Traditional Medicine for coordinating and monitoring. We are also deeply indebted to Dr. Erfani, the Vice Chancellor for Global Strategies and International Affairs, providing unfailing support all through these seminars. And we also like to express our sincere appreciation to Dr. Saha, who accepted to present in this webinar, and Dr. Zamani for providing his refreshing perspectives. Dr. Saha, I hope that next time you will be able to present your next presentation here in Iran, and especially in Shiraz. I really hope that that would be great. I hope that this. Oh, I see. And your country is also a very beautiful one, and Iran and India have deep
Yes.
culture.
I very much want to come to your beautiful country. Yeah. I very much want to come to your beautiful country because I have seen
Oh,
so
I
many movies. I have
yeah,
just seen Iran in
yeah. He
movies.
always
I haven't,
delivers very
you
profound
know.
messages.
So you know,
Yeah, they are so
yes,
deep.
yeah.
All his
Because I
films
told
are,
right, I'm
yeah,
a
actually so deep. Thank you so
because
much, and
I
I
am
hope
a
that
very
this
big fan of.
disease will be eradicated soon. The
Correct.
corona pandemic
Right. Thank
disease will
you.
come to
I
an
am a
end,
big
and
fan of
you will come
Majidi's
to
work.
Iran, and we'll
So
have
I
your
have
next
seen
presentation here
a lot
in
of his
Iran.
films.
We hope that you
Yeah.
have found this
Okay.
webinar informative and worthwhile. All the audience, I'd like to thank you. Your presence has actually made us
Right.
have a very great
Thank you
and
very much.
wonderful webinar. Thank you for your enthusiasm, for your positive spirit, which
Right.
helped make our time both fruitful and also productive. We wish all of you the best in life, and please stay tuned for the upcoming events. Thank you, and oh, you are most welcome, Dr. Mehrabi, Dr. Zarif Sanai, and all the attendees. Thank you so much. Best of luck to all of you. All the best. You're most welcome. Bye-bye, Prof. Okay, this finished.